mostly talk about nanostructure materials and physics of nanostructure materials. So if we talk about nanomaterials, so nanomaterials are the materials whose dimensions in the of the order of nanometer. So it's a 1 to 100 nanometer scale. If some object, any object whose one of the dimension is in the nanometer scale, like lies in from 1 to 100 nanometer, they are named as nanomaterials. And interestingly, the nanomaterials has different properties compared to a bulk material. For example, if we talk about carbon, so the bulk properties of carbon, the conductivity of carbon, the electrical property of carbon will be different compared to a carbon nanomaterials. So every property, conductivity, resistivity, and also thermoelectricity, so many properties could be modified in the nanoscale. And why is it so? Because of the beautiful nano-dimensional or subatomic phenomena that is lying in nano dimensions. For example, if we talk about nanomaterials, they are classified into four categories. One is the zero-dimensional, that could be particles or clusters. They are like very tiny and don't have any extent of the dimensions. They are just clustering or some one particle, two particles, let's say one nanoparticle of gold, one nanoparticle of silver, one nanoparticle of carbon. So they are all zero dimensional. One dimensional are the nanotubes, nanowires. These are one dimensional nanomaterials. You can see the screen, right?
Yes, ma'am.
And two dimensionals are like nanoplates or nano layer, let's say graphene layer, who has the area. So they are the all two dimensional nano materials. Three dimensionals are multi nano layers or a bundles of nanowires. If we arrange all the nanowires in a in a surface, on a surface, then it could be a 3D. So nano cube is a three-dimensional nanostructure. So or any aggregated tube ellipsoidal particles or the shapes which can make three-dimensional structures in the nano range, they will be three-dimensional nanostructure. So zero-dimensional nanoparticles are the particles which have the range of scale length of 1 to 100 nanometers. Just like single crystal, single nanoparticles, quantum dots, these are all zero dimensional nanostructure. And one, so if we talk about in terms of the graphical visualization, so this is the zero dimensional nanoparticles, this is the one dimensional nanowires, nanotube. These are the 2D thin films, so nanosheets. These are the 3D like cube, nanocube. And this is a carbon nanotube. This is a picture of graphene thin film. And this is a picture of 3D polycrystal of carbon. And you see, as you change your dimension, density of states are changed. Why? Because right now, the material is not a bulk material. Right now, you have cut the potential over one dimension. And the potential for the particle for experiencing potentials in different directions is different, because if we restrict nanowires, then the potential is confined. The atomic potential or potential inside the nanostructure is present only along this particular direction, or only within this particular area, or only within this particular particle. So you have restricted the electronic charge distribution within some very confined area or confined length or confined volume. Therefore, you have also restricted the potential, and you have also accordingly restricted the energy levels, because from the energy levels, if you plot Schrodinger equation, if you uh, solve Schrodinger equation, you will get energy eigenvalues, and then you will fill the energy levels with considering Pauli explosion principle. because electrons are fermions. And then you will see the density of states for different dimensions, they will show different geometry or different variation. For example, for zeroth dimensional state, you will get this kind of EG, and this is the representation of density of states GE versus E. This is a zero dimensional density of states. For one dimensional, it will change and it will shape like this. For two dimension, you will have this kind of EG, and for three dimension, you will have this kind of EG. So let's take why we have different band gap or why we have different density of states for changing the dimensions. So if we talk about nanomaterials, all of them are very confined in limited in space because of that tiny nanostructure. And if we check the different properties of the nanomaterials that I will show from here. Yes, electrical properties of nanomaterials. So if we talk about bulk materials, all the electrons which are conducting electrons, they are in the conduction band and they are delocalized. Means they are almost free and they can travel freely from within the from here and there within the bulk material itself because of its potential or surface barrier potential. And then they are kind of mostly delocalized, means they can freely travel a longer distance of entire material. Let's say we have a bulk material of 1 centimeter, so the conduction electrons are delocalized and travel throughout the material freely within that range of length. And it is also for XYZ everywhere the dimension is, let's say 1 semi, 1 semi, 1 semi. So it has all the freedom to travel freely within this one by one semi-cube structure or bulk structure. Now in nanoscale conductors, two effects will become important. One is the quantum effect, because earlier all the conduction electrons can travel freely within the continuous bands that they have as a term of conduction band. Right now, they will be replaced with discrete energy levels. So they are not traveling or they are not freely traveling within the material. Second is the classical effect. Mean free path for inelastic scattering becomes comparable to the size of the system and can lead to reduction in scattering events. So their scattering phenomena will also reduce because their mean free path also becomes small because the system size is also right now small of the order of nanometer. Because right now uh, our system is confined in, let's say, 10 nanometer by 10 nanometer by 10 nanometer. And earlier, for a bulk, let's say 1 semi by 1 semi by 1 semi. So right now we have comparable system size, which is comparable to the scattering of two different electrons. So now when we change the dimension or once we reduce the size of the material, then density of states will also change. And the quantum confinement effect is coming due to the restricted energy level that we have in the nanostructure. And this will also increase the effective band gap size because the conduction band and the valence band right now they are discrete energy levels, leading to a leading to an increase of the effective band gap. For metal, if we talk about bulk metals, the band gap is almost zero because of the overlapping of the valence band and conduction band. But here in the quantum materials or nanostructured materials, we will see there is a band gap existing between the valence band and conduction band of the material. And the effects can lead to altered conductivity in nanomaterials. So therefore, if we change the band gap, if we decrease the band gap, we will get certain amount of conductivity. If we increase the band gap, we will get different amount of conductivity because the energy requirement to excite the electrons from the ground state or valence band to the conduction band or excited state is right now different. So let's see, we have a particle in a box problem that we all know for in quantum mechanics, that if we talk about particle in a box and we see these particles in a box, we will have quantum particles associated with wave. So they will have this kind of nodes at the boundary, and this is the ground state wave function, this is the first excited state, this is the second excited state, and the particles will have this energy level E. If we talk about En or energy eigenvalue, then n square h square by 8ml square. And this L value is the length of the box. And this n value is the quantized or quantization of energy level because n can only be integer 1, 2, 3. It cannot be 1.1, it cannot be 1.2, or it cannot be 6.65. So therefore, the potential is responsible for the particle to give separate discrete energy levels because this potential will lead to certain different wave functions, and we will solve the Schrodinger equation and we will get such kind of energy eigenvalue. And this kind of potential is also exist in quantum dot. So zero dimensional potential means you are confining the electrons inside the quantum dot within this potential, box potential or quantum potential. Well, where you see these energy levels of the let's say carbon quantum dot, they will follow the rule of energy eigenvalue with n square h square by 8ml square. That is dependent on the length of the box. If we talk about two-dimensional and or one-dimensional potential well, then we will talk about quantum well. And if we talk about 2D structure, so we have this kind of confinement direction. So if there is a 2D material, for two-dimensional, it will become like at the one dimension, it is only confined. It can go up to along this direction or along this direction, along x and y, but it cannot move the z after this certain kind of width. So this is the confinement direction. So you have restricted the motion of the electrons or conduction electrons only to the surface of the particles or surface of the sheet, let's say graphene nano sheet, and that will give us different kind of energy eigenvalue, and this is the h square k square by twice m, because right now the k is restricted with kx and ky. There is no kz. And why kf? Kf written due to the highest occupied energy level, that is Fermi energy level, and kf representing the highest occupied wave vector. So it is written in terms of the Fermi energy level. And if you see the density of states, so the density of states will show like the this kind of step potentials after for each scale, and it is constant for 2D. And if we talk about 3D, we'll have density of states of the order of e to the power half. So for 2D, the density of states of the is a e to the power 0 or of the order of 0. So as we change the restricted the motion, we will get different energy levels, and from there we define the density of states and we get different density of states. So density of states is defined as number of energy levels per unit volume, right? Or number of, let me check. Just 1 minute. If I open this book, so this is the solid state physics, Puri Babbar book. And from in this book, it can be like a reference, more short reference book kind of book, which I like. You can just easily look at the book and check some topics, and you can see the overall understand the overall idea, and then you can further search it in other references. So if we talk about here the density of states, so the density of state is defined as the number of electronic states per unit energy range. Yes, not per unit volume, it is per unit energy range. dN by dE. So how do you get density of states? So to get the density of states, first you have to solve the Schrodinger equation, and then you will get E value, that is the energy eigenfunction. And from the energy eigenfunction, you will find out dN by dE. So you have to write E, or the energy value, in terms of n, because n is the number of particles which will be filled in the energy levels, different energy levels available in the system, and then you take the uh, gradient of dDE of n, means rate of change of number with respect to energy level. So how the numbers of electrons are filled within a different energies. So dN by dE, that is the density of states. And if we uh, solve it for electrons, so it's 2 into dN by dt, because they are two occupancy, so double occupancy due to the spin half and spin minus half, and then you will get the density of states for the 3 dimension. You will get this. Yeah. So if you do it for the similar thing for the 2 dimensional sheet as well as for the other 1 dimensional case, and we will check different density of states, because the energy eigenvalue distribution is different, and therefore we will get different density of states. D, dE, dN by dE. And for 1 dimensional, it is of the order of e to the power minus half. For 2 dimensional, it is order of e to the power 0. For 3 dimensional, density of state is proportional to e to the power half. So this variation will lead to the difference in the density of state, and that will give us that is coming due to the confinement directions of the free electron. So if we talk about the electron in 1D nanomaterial, so right now the energy electrons, these free electrons are confined in only one direction. This, let's say this is a axial direction. So it is only confined in this axis. It cannot go beyond this axis because the material itself is confined in this axis. And if you get the energy eigenvalue for such kind of system, you will get En, that is pi square h cross square by nx square twice m lx square plus pi square h cross square by ny square by twice m ly square plus h cross square kf square by twice m. And the coordinate you can here defined as lx and ly, and here you will get this density of state variation. So overall, the understanding is there, as you restrict the material in 1D and 2D, electrons will be also restricted according to the dimension. And the dimensions will restrict means the boundary condition will be different. From a bulk material, the boundary conditions of the potential for a quantum material is different, and also the potential expression is also different. So therefore, we will get different energy states, and that will lead to different distributions of particles into those states or density of states, and that will give us different phenomena in differently dimensions of different materials. So all this can be justified from the quantum confinement effect because of the nano dimension of the particle or of the nanostructure. And if we talk about nanomaterials properties, so this is a very beautiful PDF that I see. There are a lot of information is here. So surface effects and all. And this quantum confinement effect is very important phenomena because also the nanomaterials have a high surface to volume ratio. So if you check the other materials, let's say I should have some photo for that. So if we take a nanomaterial, it has a high surface to volume ratio. That means that its surface is to volume is larger compared to a bulk. And due to this high surface to volume ratio, it will give the surface specific phenomena. Means that let's say we have a very large chunk of iron, okay, a chunk of some, this is, let's say this is not crystal, this is a chunk of material, and it is completely closed because its surface is completely closed by all the neighboring electrons. And right now, if we start reducing the dimensions of this chunk of material to a nanomaterial, then the surface electrons, their bonds will be free to the or open to react on the at the surface because there is no one to make bond, no other atom to create the bond. So the surface atoms are or surface electrons are completely free to react or they are loosely bound to the system. So therefore they can give us tremendous different properties like they can give us more conduction, they can harvest more light means they can absorb more light, or if we excite those surface free electrons, they can also excite and give us different light at different wavelengths. So therefore, the electronic structure at the surface we have modified because if we should see the bulk material, they are already closed with all surrounding atoms due to bonding. But once we crop the material at the nanostructure, both bondings are cut at the surface, or there are some bonds which are not able to bond with some other neighboring atoms because those atoms are missing in the structure. So therefore, they are loosely bound and they are more reactive. And this surface to volume ratio gives us certain different properties of the reflectivity, transmittivity, absorptivity, conductivity of the nanostructure because the electronic structure is also modified. And that's why the nanostructure material is very important because its effect on the different material have highly exotic properties and they can be useful for different practical applications. So I can show you what are the applications for nanomaterials. Let me. So there are a lot of applications actually, and most of the things are given in a research paper form. But I want to give you in general idea. So let's say we see it from the Wikipedia. So if we talk about carbon nanotubes, so nanotubes can help in cancer treatment. So how they can helpful for cancer treatment? Because the nanotubes can vibrate with the laser. And let's say right now we use laser therapy for cancer treatment. So therefore, if we inject carbon nanotubes, because our body is biocompatible with carbon, so carbon is a biocompatible material. So the patient is injected with carbon tubes and they will selectively go to the cancer cell, accumulate around the cancer cell. And once we put the laser, the nanotubes will be excited and they will radiate thermal radiation. So the local heat will be larger and therefore the cancer cell will be destroyed or they will be like boiled, immediately boiled due to high heat. So That is one is the application. So if I show you plasmonic, this is called a plasmonic heating effect or thermal effect. So who, yes, so they can absorb. So all the electrons that are free around the surface of the nanotube, they will freely they will be excited with H nu. And since they have highly confined energy band. That is the exotic property. That they have highly confined energy band. So we can choose the laser which one to tune. And also the beauty of this nanostructure that we can change the band gap. So let's say we don't want to excite body with UV radiation because this could be very harmful. All the cells could be destroyed. But if we want to use IR radiation, which is not very damaging for the cell, but many materials don't absorb IR radiation because normally bulk materials, the electronic absorption or absorption happens in the UV range and so mostly the light absorbed in the UV to visible range. So if we have this kind of material which has a H nu, that is band gap lies within this IR region, and we excite with the IR laser, and they will absorb all the energy H nu, and then they will locally transfer the heat to the tissue or the cancer cell or cancer tissue, and it will destroy by heating. So it will destroy the cancer cell. It will destroy the cancer tissue. Immediately it will boil or cook the cancer tissue. So that is a very important potential application. Another could be industrial application. So forests of carbon nanotubes are important in space where there is more light than is convenient to work with. Ultra black material can be applied to camera telescope system to decrease the amount of light and allow for more detailed images to be captured. So therefore, for different camera setting, you can also code the nanostructures, and also you select enhance the light harvesting capability of your camera. And also there are different disease treatment, and nano electronics is another very important because everything we need right now is the nanotechnology on the chip, because you see the phone size or the say what is do you mean by nano, that has a lot of only destroy this virus. but it will not affect to other organs of our body. So this kind of, how do you do that? Because nanomaterials, we can make it target specific, and if we label it with um, uh, proper channel, let's say the virus has a antibody, has a protein structure on its surface, and the nanomaterials has an antibody within its surface. So that antibody having the nanostructure, we will only go and target to the virus, which will be which is responsible for the cold and cough or for the disease. So therefore, it will destroy because the nanoparticle has also the healing capability. So it will destroy the particle and it will go target specific and destroy. So therefore, will not other side effects. So there is a this era is a transition change in biomedical field, biotechnology, nanomedicine, and also therapeutics. With the nanoscience and nanotechnology, we have a huge application here in the field of nanoelectronics because we see all the chips right now are very, very compact, small, and it will be even smaller and more efficient. And another way is the biology or biotechnology that all our devices for medical systems and also the therapeutic system like laser therapy, radiation therapy, or surgery, or different side effects. That is also going to be finished with the application of nanobiotechnology. So, we being the physics students, we have the opportunity to work in this field because we have the knowledge of quantum mechanics and physics. So, therefore, we can contribute to the nanoscience and we can arrange our devices for the betterment of the society. So, this is a very important field, and also most importantly, energy application of the nanoparticles is another very emerging area. Why? Because right now we know the energy sectors like coal generation, coal from energy generation from coals or energy generation from petroleums, they are limited. Or in fact, we also suffer a lot of inflation because of the increase of um, petroleum price, and this is the petroleums are mostly coming from other countries, and the international price market is on their control. So we have no control to reduce the price. But what we can do, we can control on the means of the way of energy generation. So one of the emerging sector for energy generation is the solar cell, because in India we have a power of sunlight. We have two, 12 months of sunlight, enormous amount of sunlight, which most of the Western countries don't have, and many of the countries don't have that amount of solar energy in through the entire year. So therefore, with the nanostructure materials like solar cells, we can harvest sunlight because the surface property or enhanced electrical property, the electrons will be ejected with the proper radiation, with the photovoltaic effect or photoelectric effect. And then if we have some external circuit, then it will flow and we will have photo current. So this solar cells could be extremely important, and we right now we have in the market that are silicon solar cell, but with the nanoparticles or nanostructures, we will have more efficiency. Let's say we are using a bulk silicon, and then we are using a silicon nanowire. So the bulk silicon, the surface to volume ratio is less, and silicon nanowire has surface to volume ratio is more. So what do you mean by that? Let's say if we see the silicon nanowire structure, you will see within a small volume there are a lot of surfaces at the nanowires which are free to interact. So let's say we have only a bulk silicon. We don't have this much of electrons per unit area for a bulk silicon, because for bulk silicon only the surface is responsible. But if we have a silicon nanowire and we have a array of silicon nanowire, all these nanowires, all the surface of the nanowires, there are free electrons and they can be excited and they can come out of the surface. So overall electrical conductivity will be increased. So that is the beauty of nanowire. So this is the picture. So if you think you have a whole silicon, so you don't have such a huge number of free electrons on the surface. But right now we have a silicon nanowire, so all nanowires they have free electrons on the surface, and either it will contribute to the conductivity of the electrons and it will generate photocurrent. So it will lead to more efficiency. So these exotic properties of the nanomaterials also can be used for hydrogen fuel cell. So let's say right now car is we can like the consuming the petroleum, and certain some of them are electric car, but it can be if we have hydrogen fuel cells, so we can use it can also it can be eco-friendly because it will not emit any CO2. So this can also be done from we have some, let's say we have water and we have some nanostructures, and we can split water into H2 plus OH minus. So H plus plus OH minus, from H plus you will make H2. So from water you will create hydrogen gas. So the what is the fuel? The main fuel is your water, and from water, using your technique, you are using hydrogen. You are making hydrogen, and this hydrogen will be useful for the car, for the energy for to give the car. So that is a very important topic, and also the different batteries, because lithium-ion batteries right now are the primary electronics, but the batteries can be like they have potential dangers because we see that they are all time and most of the time they are getting heated, and also there are several explosions happen due to the lithium-ion batteries. Mobile explode or some other explosion happens due to the high heat. So if we replace this kind of batteries with some graphene batteries, that will have more capabilities than the current battery, and more stable life. So more energy generation is a one of the major sectors. So these are all practical applied physics applied physics zone where you can directly apply your technology to the improvement of the society. One is the energy application, so energy sector. Another is the health application in the health sector, and another is the electronics sector, and also in the construction sector. So different construction development, steel, wood, glass materials could be modified, and they could be more sustainable compared to the bulk material, and also in different fields. So this is the example of carbon nanotubes, but this kind of nanomaterials can be used with graphenes, carbons, with gold, silver, and all different quantum dots of different materials are also useful. For example, silicon is also another useful um, way to material for nanotechnology. It is also useful for sensor because all these electrons present at the surface, they are highly sensitive. So if some chemical is, let's say, they are reactive with some particular chemicals. The electrons present in the silicon are reactive with some particular chemicals. So therefore, that will become a sensor for the for sensing the chemical. So if there is some industry and if we have some, if we need some sensing device that will sense certain toxic materials. So we will design our material nanostructure in the sensor that nanostructure, the electrons will sense or react to those gases, and it will give us certain alert in terms of the leakage of the gases, or many of the structures can be useful for alcohol sensing. So if someone is driving car with alcohol, after drinking alcohol, so this can be also sensed using different sensors. And these are the different portable devices. And for example, let's say if we want to uh, detect corona. So right now, coronavirus or COVID-19 is detected by RT-PCR or some means that requires a lot of time. But if you have some sensor which can immediately tell you what is the name of the bacteria, whether it is corona or not, then you see the pandemic would be restricted, like the because of the within some time, let's say 10 to 15 minutes, 20 minutes, you see the result, and according to that, the advisement or care will be taken further preventing the spread of the infection. So this kind of health sector, and also the cancer treatment is very important because right now cancer is right now disease diagnosed after third stage, fourth stage, like when the patient has very less probability of chance of longevity. So therefore, and the also therapy is very painful. So if we could have some medical devices that will give us immediately the result, and also the detection of cancer in the early stage, if it is possible, then maybe lot of the people will get benefit from the devices. And also the therapy, if it can be restricted to certain target specific cells, it is not destroying, if it is not destroying the whole cell, or if it, the surgery needs to take the doctors needs to cut the whole organ or whole tissue. If someone is having a breast cancer, the doctors usually cut the whole breast. So this is a very important problem for the society, that we need to be more specific to our medical tools, and that can be also modified using nanotechnology. So therefore the lot of work is happening at the nanoscience and nanotechnology, and you see each of the department has different faculties, or in fact many departments dedicated to nanoscience and nanotechnology is already established. So this is another way to get and have your research in this field. Okay. So any question?
No, ma'am.